Hello everybody, I'm your host Hal Curtis and I'd like to welcome you to The Space Industry by satsearch, where we share stories about the companies taking us into orbit. In this podcast, we delve into the opinions and expertise of the people behind the commercial space organisations of today who could become the household names of tomorrow. Before we get started with the episode, remember you can find out more information about the suppliers, products and innovations that are mentioned in this discussion on the global marketplace for space at satsearch.com.
Hello everybody and welcome to today's episode of the Space Industry Podcast by satsearch. I'm joined today by a couple of returning guests, Michael Seidel and Adrian Hellwig from global electronics manufacturer Texas Instruments, a name you're probably very familiar with in the industry. Now today we're going to talk about key enabling technologies for next generation satellite communications payloads. The satellite comms payload sector has seen a lot of innovation over the last few years. But there's, as always with everything in space, there are areas where there's a lack of standardization, and there are plenty of decisions that individual engineers need to make when developing their own missions and technologies. So I'm excited to get into this topic and see what the insights are from a company like Texas Instruments, or TI for short. Firstly, Adrian and Michael, thank you very much for being here with us today. Really good to have you.
Yes, hello.
Hello, and glad to be here again.
Fantastic. So the satellite communications market has evolved quite a lot over the past couple of decades. As I just mentioned, we see a lot of innovation in this area. Now, from your perspective, what do you think are the key changes you've observed in antenna technology and the RF signal chain, as these are really key components in the communications, architecture for a satellite? I think to Michael, if that's okay.
Yes. And yes, indeed. There have been really dramatic changes and advancements over the past 1 or 2 decades in this area. All probably on the main driver behind that is about people have the hunger for higher data rates and need to handle more and more channels or more users in parallel. And plus, speaking satellites, there is now a significantly reduced cost per launch. And that makes now the LEO constellations highly attractive. So there's also a major change in how these systems are implemented. Now, if we take the topic of RF sampling, right? So people try to sample the data directly at the high frequency without intermediate frequency. And that means, of course, you need a very high-speed data converters. And the amount of data being now much higher, you need to then also have very powerful FPGAs or computational power afterwards. And speaking that RF sampling, people now also on top of it moving to higher frequencies that make the problem even worse. And now we're talking about X-band in RF sampling, going to the 8 to 12 gigahertz band, and that even with a high instantaneous bandwidth that is well above a gigahertz. So you see this extreme increase of sample data now that needs to be processed. And now we're looking already as of today in really the next generation of super powerful FPGAs. Of course, also being very power hungry or electrical power. And now, as that would not be enough, there is now, when you look at the industry, we have multiple endpoints that one satellite wants to serve at a time. So you have a routing capability is now also needed in the satellite. So you need that intelligence there. And having multiple users in different locations. So connecting these in different locations. But as we said, we are not any more geostationary. We're in the LEO orbit. So our satellites have a fairly fast speed over ground. And that means your antenna has to move with the users or for the users. And you need to fastly hand over between the satellites. And of course, all these users are in different locations. So that makes it a lot of complexity and also a need for moving your antenna very, very fast and precise. Now, probably the only way to overcome that challenge is by people moving to the phased array antennas. They're also known as electronically steered antennas. These antennas are the ones that really enable the beamforming as a main keyword we need to mention here. So these phased array antennas come with a couple of real good advantages, right? The first one, as the name says, also is the fast electronically steering of the antenna beam. Now, even you can do multiple beams, right? You can connect with one array of these phased array antenna. You can connect multiple users in different points and have multiple beams. And another thing that comes to it is like the increase of antenna elements allows you then also to better focus the antenna beam towards the receiver. So you have a higher antenna gain. So there's good things about it, but talking about increasing the number of elements per antenna, that also increases the complexity and overhead of the electronic design, as each of the elements have to be built with their own receiver and transmitter. And now when you look at the higher frequency bands we want to go to, is also there is a relationship. The higher the frequency, the lower the bandwidth, and the lower the spacing between those elements. And that means it's getting even more dense for the electronics behind it. So you have here another challenge on space, on board area, but also about dissipating the heat that may come from the electronics themselves as power losses. Yeah, and like if this would not be enough of a challenge, there is even getting things even worse. We're talking, or people really want to make sure that the cell phones can also connect to the satellites directly. Cell phones, of course, come with a very small antenna. That means the antenna gain factor in space has to be even larger than, right? So I'm speaking about an even larger number of elements per user and of the phased array antenna. And now also when we think about you have a cell phone and you want to send a high-speed data to each of the cell phones, that means then also you have to increase the radiation power itself. So here again, a increase of power requirements we having up there in space. So to summarize this all, so you say the sampling rates going up because we do the RF sampling in even higher frequencies. The number of elements per phased array antenna have to go up, and the board space is getting smaller per element. So the power density and the load board space are the key requirements for the electronic components that we need to build there. And when you look at what TI is doing here, we have a strong focus on the high-speed data converters, the high-frequency clocking with extremely high quality, and also what we're also constantly looking for other functions we could integrate or improve to help on the integration level. Like there is now an example, what we call the active balun. That's the TRF 0206-SP. That is a single RF amplifier that replaces the bulky balun and the gain block altogether and comes with an even better linearity. So there's also, beyond the data conversion and signal processing, we provide here a lot of innovation.
Wow, thanks, Michael. I think that's a really good overview of the problem. I mean, we work a lot on helping companies, understand where their market is and position themselves in the context and the storytelling. And particularly when you're talking to people outside of the industry, it's very attractive to use analogies with computing on the ground. And in this situation, I think you've illustrated that analogy falls down pretty quickly when you consider that satellites used in conjunction in constellations or with routing requirements are not stationary. They are not connected with cables. These problems are much more much greater significance in orbit than they are on the ground. So the applications and the different modes of operation that you can follow need to adapt, and that starts with adapting the components that you're using. So thank you. That's a really good introduction. So you mentioned that obviously the additional complexity is requiring components that need more power, and you mentioned more powerful FPGAs as an example. I wonder if, Adrian, you could give us a bit of an overview of the kind of latest power supply and power generation capabilities that are required in satellite communication systems today.
Yeah, sure. I can do this, and that's also getting complex in that field. So, and especially we see a one trend. Those high performance FPGAs are being used for those systems, and there are, let's say, two main reasons to do this. And one of them is high amount of data being processed. but also at the same time, the interfacing capabilities. Because as Michael mentioned, for all those RF sampling ADCs, DUCs, and analog frontends, you need a special interface to connect to FPGA. And now at the same time, those FPGAs are really power hungry. So as an example, the newest AMD Versal FPGA requires only for a core rail 100 and more watts. And at the same time, the voltage for this core rail, in this case 0.8 volt, is going down with each FPGA generation. So all those specification changes really putting extreme tough requirements for power supply design. And to support those needs, we offering different solutions. One of them is, for example, a combination of rad-hard controller, like the TPS-7H5001, and rad-hard GAN FET driver, TPS-7H6003. So that's for the core. Now, if you think about other rails for those FPGAs, and believe me, there are many for this FPGA, so customers can work with lower current point of loads converters. And I have here especially in mind the very well-known TPS-5601A, which supports up to 6 amp. Or if that's not needed, customers can work with TPS-7H4002, for example.
Okay.
Now, if you look at the sensitive loads, customers may need an LDO for it. And here we just released a so-called RF LDO, TPS-7H1111, which is a device with extremely high power supply rejection ratio. So customers can work with that. And if that's not needed, there are still very well-known devices like the TPS-7H1101A with 3 amps, or the TPS-7A4501 with 1.5 amps. So it's really a complex task to develop efficient and reliable power supply for those FPGAs. But we can support customers with a wide range of solutions, also for different radiation requirements, not to mention availability of samples, evaluation modules, DEMI packages, or collaterals like app nodes, reference designs, and simulation models. And by the way, we support both PSpice and Simplis here. So that's also very important to mention. So now, if you think about this, we don't really know where the journey will go, but we definitely see an increase in power requirements, since that's really demanding. It's so demanding to dissipate the heat in space. So it's really required to design very efficient systems.
Yeah, absolutely. And I think, as you've highlighted here, everything in space comes with a trade-off. So higher power equals, greater performance, supposedly, but more heat and more power, generation requirements, which takes up or can take up more space. So every satellite is structure and setup is evolving mission by mission for every company, I think. And it's very interesting to see how these trends go. So thank you for that. We'll obviously link to some of these materials and things you've mentioned there in the show notes as well for the listeners. So now, Texas Instruments has also made a bit of a name for the design and manufacture of semiconductors and integrated circuits. I wonder if you could share with us the sort of product lines and areas that you're using to serve this market in space and communications payloads, and how the company is helping to push the boundaries of innovation and bumping up against these limitations that mission designers and engineers are meeting.
Yeah, I think the way probably to answer this best is looking at it is like when it comes to innovation, there are probably multiple dimensions. And let me start with the first one, which everybody probably has immediately in mind, is performance, the pure performance. Like, for an example, you take gigahertz clocking. Here, a device like the LMX2615-SP, that is a 40 megahertz to 15 gigahertz wideband synthesizer with phase synchronization and JSD204B support. Here, for example, this has a high performance PLL with a figure of merit of minus 236 dBc per hertz. So this is a very low in-band noise and jitter performance that is kind of unheard of before. Then you have maybe what Adrian mentioned before, the ultra noise LDO, right? That is really a power, enables a power supply that really limits the power supply generated noise and the phase noise and the clock jitter to an extent that you can call it really an ideal power supply. And that helps also a lot in your system optimization, as there's simply one thing less to worry about. You just know whatever it is that degrades your performance or keeps you away from the optimum is not the power supply. So that's our key enabler here. Or what we discussed also from the beginning of the call is power density, right? And getting higher power density. Here's a device maybe like the TPS7H4001-SP. That is really a DC-DC converter that, depending on the use case, it's up to double the power density over its nearest competitor. So really a major step ahead on that topic. Or Adrian did also mention the latest gate driver and PWM controller for GAN. Having GAN available in space is, of course, also a major innovation step in getting the power density up and the power efficiency up. Or look, high-speed data converters and analog front ends. There's the ADC 12DJ5200-SP. It's a 300K rad, 12-bit dual 5.2 gigasamples per second, or a single channel 10.4 gigasamples per second ADC. Also here, really opening very new applications, and especially also for RF sampling ADCs. Or coming to an extreme example for integration, there's the AFE 7950, also available for space grade. That is a 4 transmit and 6 receive RF sampling transceiver for up to 12 gigahertz. Believe it or not, 6 transmit or 6 and 6 receive channels, and with a maximum instantaneous bandwidth of 1.2 gigahertz. And yeah, with integration, I'm already in the second dimension, right? When we talk about integration, there's maybe a very different example here for the power amplifier. These power amplifiers need a very accurate bias voltage, and that also has to be adapted permanently according to the temperature and power level. And here you have really a need for multiple DACs and ADCs. And here comes a device very handy called AFE 11612-SEP. That has 16 ADC channels and 12 DACs integrated, plus temperature sensors and several GPIOs. So that really enables customers to quickly design things and do not lose a lot of board space, and still have that very good and needed capability to optimize your solid state power amplifier design. And a very different level of integration and a different kind of is maybe when we talk about our space grade lockstep MCU, the TMS570 LC4357-SCP, also called Hercules in the industry. That has built-in diagnostic capabilities, and these built-in diagnostic capabilities help us a lot in this FDIR topic. FDIR, the fault detection, isolation, recovery. That is what our designers have to build in there. And the interesting thing about this device is there we were really bringing those risk mitigation capabilities that have been originally developed for functional safety, in this case really for an ABS and power steering in the automotive industry, and we bring that integration for space and bring that value now also for our space designers. So that's really a new approach of bringing the system level resilience up. So not only as traditionally from bottom up, from the component level radiation hardness and robustness, we also come top down, that we have more intelligent and more complex fault detection, isolation, recovery strategies there. Now, so we have, after those dimension of performance and integration, now the third dimension I would call packaging. And that might be these days probably the most significant one to mention. We're very, very happy that the Defense Logistics Agency, the DLA, has approved now what we call the QMLP standard. So that really allows now plastic packaging for space. We're particularly proud of it because TI made major contributions to that standardizations. And we also leverage here a lot of our experiences from what we call the SEP portfolio, the space enhanced products we have on the market since quite a while, that is specially targeted for LEO constellations, where we actually balance the radiation hardness versus the cost. And these devices come already in plastic for several years. But now the great thing is we have plastic packages also allowed for Class 1 missions, similar to QMLV, really just staying side by side to QMLV RHA. Now, why I'm so excited about plastics, there are so many advantages going to plastic packages. The most obvious one is, of course, it's a much smaller footprint over the ceramic packages in QMLV. Now, the nicest thing even is if you have what I call the SEP, targeted for the LEO constellations, and now the QMLP for traditional space or deep space or geo missions, you have one investment, and the pin compatibility between those two allows you to either serve the LEO or the geo market. So that's also a great thing to have here, this pin compatibility between different radiation hardness levels. Another thing that makes your life much easier is you look at ceramic packages, they come with these very long leads, and they first have to be formed and trimmed, sometimes even in an outside company. And with plastics, you don't need this anymore. That is pre-formed and pre-trimmed. That is now allowed because the lower weight and the smaller dimensions do limit the mechanical stress upfront, right? So you have lower weight, which resolves your vibration concerns, and you have a lower dimension, which reduces your concerns on the different temperature coefficient between the PCB and the component. And yeah, I have even more two more items to mention on the plastic packages. The next one is that when it comes to integration, right, we can in plastic, we have a lot of experience now over the past decades, as this is, of course, what the majority of the industry is using, that we can do multi-chip modules easily. We can integrate the decoupling capacitors, other components, transformers, inductors, right? We can even in 3 dimensions integrate things. That is all technology now we can start looking at in making those things also available for space, where before for ceramic, we were quite limited in that one. And the very significant for our topic of satellite communication payload is these smaller dimensions and these shorter bond wires, they do also reduce the parasitic capacitance, the inductance and resistance of these chips themselves. And that directly gives us a better performance in the RF area, but also in the power supply area. And as we spoke before, these are the 2 major concerns, of course, right? RF and power density is what we need to improve constantly. And this is where, again, our plastic packages help us a lot. Maybe to mention just here an example, I had this example before, the TPS-7H 4001 SP. And I told you that is already double to the nearest competitor in the industry when it comes to power density. Now, if I take that device from ceramic into plastic, I get a 2.5 times better power density on top of that. So just to show that is really significant, maybe you can see and understand my excitement about that. So to summarize it all up, right, this is like several dimensions in innovation. It's the efficiency, it's the power density for the power supply domain. It's the ultra low noise and the extremely high speed data conversion and very low jitter noise on the gigahertz clocking solutions, the RF domain. We're integrating self-diagnostics, and as just on my last item, don't forget about the packaging technologies, where we have now so many more things to do moving forward.
Fantastic. Thank you. That's a really good overview of the innovation, the area. And I think You mentioned all the benefits that brings, and another one is obviously versatility from the mission designer's point of view. If they can do, you mentioned how some of the components enable that, but if they can do more with less, essentially, I think that's an important thing for lots of mission designers in the future. And another example of that to follow on is we've observed in NewSpace that new market verticals are opening up, such as laser communications. Now, we focused on the RF sampling, etc., but I wonder what your thoughts were on high performance electronic component requirements, which is obviously TI's sweet spot for this area of the market, for the laser comms subsystems we're seeing.
Yeah, that's also a very, very good question. Yeah, and an interesting new market, and we really see in here a lot of new players, especially for this high performance solutions for laser communication. And now, if you look at laser communication and radio communication and compare those two technologies, you immediately see that the precision of the transmitter and receiver pointing is much more demanding for laser communication, right? And so to achieve this, you really need a precise motor control systems. Michael already mentioned a lockstep MCU that can be used for this task, TMS 570 LC4357. So this device is offering really a motor control specific features, so customers can use. Now, but not only processing, but also the analog regulation is very important, right? So to do this, you need, for example, to measure a current in each phase of the motor. You need a very precise measurement there. So here I have in mind a current shunt monitor we can offer to our customers, INA 240-SEP. That's a device with extremely high common mode voltage range from -4 up to 80 volts. So that's one possible solution. Now, if you look at the laser receiver system itself, we also see here a need for higher speed data converters and obviously clocking devices like already mentioned by Michael. And this will enable higher modulation density. We already heard from Michael about some of the devices like the ADC 12DJ 5200, RF sampling ADC, or if you need even more integration, the AFE 7950, which is our multi-channel transceiver, can be used here. At the same time, which is obvious, you also need a good clocking solution for those ADCs and AFEs. And we heard already about the full space solution synthesizer, but we also have something to offer for a space EP. And here I have especially in mind the LMX2694, which is really the equivalent device to the already mentioned that LMX2615, offering 15 gigahertz of output frequency. Or if customers only need to distribute the clock to different ADCs or analog front ends, they can work with a device like the LMK04832, which is our high performance clock conditioner with 14 outputs. So a lot of different solutions we can offer here, customers working with laser communication systems.
Excellent, thank you. I mean, yeah, an emerging application in satellite communications, but obviously one that seems to be that there are plenty of options to account for it, at the least at the electronic components level. So it's really interesting to know, and I think important for engineers out there factoring these technologies into their designs. Now, just to follow on a little bit and to keep on that same vein, Europe's flagship connectivity program, the Infrastructure for Resilience, Interconnectivity and Security by Satellite, or IRIS-2 for short, is said to utilize quantum key distribution capabilities. Can you tell us how power supply and generation, requirements will vary for this sort of project, given that quantum key distribution will primarily serve high security demand markets like defense and intelligence due to its very nature.
Yeah, I think when it comes to the quantum key distribution, the way it's typically done today is you generate entangled photons, and those entangled photons have to then be actually sent out or distributed to the endpoints. Sending those photons, it's laser communication in space. There are no fibers from the satellite to Earth. So it's laser communication. So anything that Adrian just said fully applies here to the quantum key distribution, and what challenges or what portion of those challenges we can address from our side and support. The other angle I want to bring up here is like when you talk about security, it means you have to stay ahead. You have to stay ahead of your competitors or those hackers or enemies that try to break into your system. So even if we consider quantum key distribution very safe as of today, and we wouldn't know how to break it as of today, but we all know we must not be naive, right? Things will move on and people find ways. And ultimately, that means to the developers that you have to keep up with the newest technology, and you must be able to develop fast, and you need to be able to come fast to a deployment scenario. It doesn't help you if it stays in your lab. You need to bring it really into the space and update things there. And our answer from the TI side to that is what we support here, a fast development with the help of what we call a catalog business approach. So all the parts we provide for space, they are readily available for development. And that means these are fully characterized and documented for the space usage, right? We're not just making outlooks. It's all there. We have all the quality and material reports readily available over the internet. And also what we do on top, we publish the inventory on pricing on these parts, and we deliver them from our online store within days. So customers are really sure whatever they decide for here, they can rely on it and they can purchase it. They receive it immediately. They know what it is from day one and be able to order as many units as they really want there and need there. And that's the one thing. Then, of course, we want to get our customers quickly in the development and get them really at the right starting point. So therefore, we provide a lot of application material and also reference designs. So there's not much time lost in trial and error. And on top of it, we provide a very technical, strong support, be it from our FIE community or also the E2E forum. And I want to say, if it calls E2E forum, it sounds a little bit like a call center, but I say not at all, not at all. The E2E forum really brings you directly to our experts in the product lines, right? They are really our back-end support, and you cannot find a stronger expert on the parts than those who have it designed. And they are there to respond on the E2E forum within 24 hours. And what I said before, keeping up, being fast, the plastic packages, QMLP, our standards or SCP, not only our customers, also us, we have to make sure we bring latest technology fastest as possible to the market. And here again, plastic helps us a lot here, because if I have a technology available in a commercial part and typically in a plastic housing, of course, if I can move this into space grade, but I can keep the dimensions similar or possibly even the same, it's a much easier task than if you ask us to move to a ceramic package where all these new parasitics come into the game and the leads are much, much longer. Then we have a much higher effort in front of us that we need to verify all those things and overcome new problems. That moving from plastic to plastic is, of course, a much faster way of it.
Excellent. Thank you, Michael. That's very interesting. I think the design and development speed as a factor has not really been something that space mission designers and engineers have had to deal with so much. I mean, it hasn't been possible because of launch cadences and prices and funding timelines from agencies and that sort of thing. But increasingly, it is becoming important. I mean, you look at someone like Starlink, if the amount of satellites that are launched just for one constellation regularly. So, understanding these issues from a supplier's point of view is really useful, I think, for engineers out there. So thank you for that. Just finally, I think a question to Adrian. what do you see as being the most likely next level of evolution in satellite communications, and where do sort of opportunities and risks lie for manufacturers and integrators in the coming years?
Yeah, I think we already talked a little bit about this. So for sure, something like RF sampling at higher frequencies, so going up to K or even Ka band. So that's for sure one of the next level evolutions we can see. And now, on one side, this will for sure greatly simplify the RF front-end architecture, but those higher frequencies brings also new challenges for higher speed clocking and processing of the data, right? What we also see is that the number of elements in the antenna system will also increase in the future because of beamforming requirements. So this means, and that's also opportunity at the same time, more channels are required for data converters, right? So that's something we need to offer to our customers. And now we also see a change in launch cost. Those will go down, allowing for even larger constellations in the future. And this is providing even more system level resiliency and at the same time more redundancy because you have more satellites available at the same time.
Sure.
What I was already mentioned before, the important role of inter-satellite communication is really important to mention here. As an example, nanosat or small sat, so the IRIS-2 backbone to Earth. So the number of laser communication systems will for sure increase in the future. So that's something we can see here. Now, as a semiconductor manufacturer, we need to react very fast on those markets, and especially when considering the NewSpace projects, because this will allow our customers to build communication systems with newest available technology. And that's also important to mention. This includes also an aspect of security, right? Now, if we think about risks, I think, or I would like to mention maybe three. So cost, thermal management, and predictability of development time. Now, if you think about cost, definitely what we can see here, low Earth orbit changes the game here because lower launch cost and more satellites available at the same time. So the customer needs to balance between cost and durability. And now the second aspect is thermal management. That's very important because you can imagine with every new generation, there are more and more functions implemented in your system. But at the same time, you need to think about how to get rid of the heat in space. So that's really important to consider. And the development time. And here I can only repeat what Michael mentioned. TI can help with our catalog approach. So availability of components, all the documentation available online, everything from ti.com. So that's something we can offer to our customers here when talking about minimizing the risks.
Excellent. Thank you very much. I think that's a great place to wrap up the conversation. You guys have shared with us some really useful insights into how satellite communications technology is evolving and even pushing the innovation boundaries of subsystems and payloads in areas, and how electronic components and power systems have needed to advance in line with these sort of market demands. And more broadly, how the fact that we've touched on engineering concepts and supplier concepts like your catalog approach that will actually enable more rapid development and testing and deployment of space systems. And in the case of security applications, Michael mentioned also that this is not just a nice to have anymore, it's becoming necessary in order to keep up with adversaries, with competition, that sort of thing. So thank you both very much for the insights you provided. As I mentioned, we'll share more information in the show notes and links to TI's materials and product information. There's plenty of places where, as has been discussed, there's the reference designs and the E2E forum and information about all the products that TI is obviously making a great commitment to publish openly and to share with the community. So that's very useful for everybody. So on behalf of all our listeners on the Space Industry Podcast, we'd like to thank you both very much for sharing these insights today.
Thank you very much.
To all our listeners out there, thank you very much for spending time with us. Look out for the show notes and the information you can find on Text Instruments' portfolio, and stay tuned for the next edition of the Space Industry Podcast coming soon. Thank you very much.
Thank you for listening to this episode of The Space Industry by satsearch. I hope you enjoyed today's story about one of the companies taking us into orbit. We'll be back soon with more in-depth, behind-the-scenes insights from private space businesses. In the meantime, you can go to satsearch.com for more information on the space industry today, or find us on social media if you have any questions or comments. To stay up to date, please subscribe to our weekly newsletter, and you can also get each podcast on demand on iTunes, Spotify, the Google Play Store, or whichever podcast service you typically use.